Hey everybody, a problem like this is often seeking an answer. In this particular case, since we're doing modulo 7, it's seeking an R between 0 and 6 inclusive. It's kind of the default instructions, okay? And that's because if you divide any number, no matter how large it is, by 7, you're going to get a remainder between 0 and 6. You would get a remainder of 0 if it was a multiple of 7 in this case, okay? But here we're actually looking for a value of R between 9 and 15. No big deal, really. It's just we have to find another congruence class, so to speak. But in any event, let's move along. Again, a summation of a bunch of really large numbers. For example, 36 to the 8th power is one of the summands. All right, so again, it's going to be a super, super large number that would be virtually impossible to do manually. So let's get into the solution here. Now, probably the key step in the whole problem is right here. We rewrite it like this, but we're motivated by the fact there's something called Fermat's little theorem. We'll use I. A is the prevalent letter here, or the common letter, but A to the 7th is, or I to the 7th is congruent to I mod 7. Okay, A is kind of the default letter that people use in number theory textbooks, but let your A be the I. And so see how this I to the 7th literally gets replaced with, well, right here it would be replaced with I times I. Okay. And that's because this I to the 7th literally is the same as I mod 7. You can check it out. Now the version you're familiar with, you might have seen this version. It's essentially the same thing, slightly different initial conditions. I to the 6th is congruent to 1. You can think of dividing through by I. You know, if I is relatively prime, I guess, to the modulus. But in any event, this is congruent to 1. But this is the mild restriction that I can't be a multiple of 7. Okay. Here, if I is a multiple of 7, you just get 0 over here. So this is true for all integers I and all prime numbers P. This is some slight constraints here. Okay. So, but anyway, this condition from Fermat's little theorem gives us this condition. You know, again, I to the 7th gets replaced with I squared, right? And so now you may know that this super common problem, you see this in a calculus class when you're doing integrals quite a bit by definition. But notice that all we got to do here is just hand this problem off to, because we have the sum of the first 36 squared numbers, right? So this would become a congruence. And notice how it is important whether you use equal or congruent. Some people are a little sloppy, myself included, but this would be congruent to replacing 36 right here. You would get 36 juxtaposed with 37. Okay, and then 2 times 36 plus 1 is 72 plus 1 is 73. Okay, and then this is all over 6. Okay, and probably actually technically this sum end right here, we can put congruence if you want to because we're doing mod 7, but anyway, maybe better suited to put an equal sign here. But anyway, this is equal. Now we'll put an equal sign. I should put mod 7 here just to justify the congruence, but anyway, we won't be too picky about it. So this is 6 times 37 times 73, right? Okay, but now we can switch back to congruence. 6 is already less than 7, right? But notice this would be congruent to 6 times whatever you get when you divide, whatever remainder you get when you divide 7 into 37. Well, 37 is 5 times 7 plus 2, so you would have times 2 here. Okay, now what about 73? Well, that's easy to see. You would get a remainder of 3, right, when you divide 73 by 3. When you divide 73 by 7, excuse me. So you get 3 right here, and so that's 12. And this is, now we're going from congruence to equal, right? This is what 3 times 6 is 18, 36. Okay. Now guess what? We got to switch back to congruence. When you divide 7 into 36, you get a remainder of 1, right? 5 times 7 plus 1 is 36, right? So we get this. Now this isn't our final answer, but I mean, it's going to produce our final answer. Notice we need to use 1. We need to find something in this range that would also be congruent to 7. Well, that would be 1 plus 2 times 7, right? Or, yeah, we can write 2 times 7. Some people are make a big deal about the order here. But, so that would be equal to 15, right? 15 is definitely congruent to 1 mod 7, and it's within the prescribed directions here. So that's the answer, ladies and gentlemen. Again, Fermat's little theorem got used. Very, very helpful here. And again, this is normally written a to the p. You want to, the general form would be a to the p. Fermat was a lawyer and had a lot of interest, and he apparently was one of the first to notice it. I'm sure others noticed it, but he got a lot of historical credit for it. Okay, mod p is the standard form for that. And the nice thing about it, it's one of these things where you don't have to worry about the quantifiers. It's true for all integers a and for all prime p. Okay, you can check it out. I mean, it's a cool little proof too. But in any event, this is the answer to the problem. Thank you for viewing.